All right then. Tuesday, March 7th, 2023, Seattle, Washington. Well, today what I've found and I've been reading is this nonlinear electromechanical effects and applications by G.A. Maugin, or Maugin, from World Scientific. World Scientific is a pretty good publisher, kind of like Nosen Reinhold or Springer Verlag or North Holland, Academic Press, Chemical Rubber Company, SIAM, NOTAM, IUPAC, these kinds of things. Now, in terms of what is physics, and from the 70s, that I think some of the most fruitful and prolific times of physics were the late 60s, the early 70s, the mid 80s, about 1992. And since then, there's been a lot of papers written and this and that, but a lot of the fundamentals were already kind of put in place at that time. So I'd like to read to you today a few pages from the beginning of this book. And what it is it's a series in theoretical and applied mechanics. It's edited by RKT Sia. And some other volumes in this series in theoretical and applied mechanics are nonlinear electromechanical effects and applications, this one. And then volume 2 is on the macroscopic foundations of the continuum mechanics of solids by A. Asghar. So it begins, it's from World Scientific, and it's published University of Paris, France. Let's see here, distributed by Taylor and Francis, John Wiley and Sons, DA Book Party, Allied Publishers, by Maugin, and here in, it looks like 1985 actually. See, now these were originally written earlier, but this is when this book is from. And the foreword begins this way. The nonlinear continuum mechanics of electromagnetic continuum has developed greatly in the last 2 decades. The present series of lectures, especially prepared for the University of Genoa in Italy and the Royal Institute of Technology in Stockholm, aims, in the particular case of the electroelasticity of piezoelectric dielectrics, at showing the relevance of nonlinear effects for technological applications useful in signal processing and experimental devices, transducers, resonators, convolvers, sensors. On certain occasions, one wants to benefit from the nonlinearities. On other occasions, one wants to avoid them. The control of such effects and their prediction thus is of importance. It is only with the rigorous development of nonlinear continuum electroelasticity and the introduction of certain methods of applied mathematics, developed to a large extent in the 1960s onwards, that the problems approached in these lectures could be satisfactorily solved. Indeed, the nonlinear effects require good form invariant theory, which only recently developed as a result of achievements by R.A. Tupin, A.C. Erringen, H.F. Tiersten, and others, while the exact solution of nonlinear problems, a priori involved, if not impossible, had to be replaced by results from approximate asymptotic methods, which, while their initiation goes back to Henri Poincaré and his contemporary fellow astronomers, were only recently improved by applied mathematicians, especially in fluid mechanics and nonlinear acoustics, to the extent that they can be successfully applied to wave problems in deformable solids. Present lectures are illustrated by numerical and experimental results. The latter were obtained at the CNRS Laboratory of Physics and Metrology of Oscillators, Professor J.J. Gagnepin and Dr. M. Planat, Besançon, France. These lectures are devoted to the case of dielectrics, i.e. non-conducting media exhibiting no net-free electric charges. Developments in progress by M. Planat, M. Dehar, and the author generalize the present results to the more involved case of piezoelectric semiconductors, where nonlinearities play an even more important role. The subject matter of the lectures touches upon various facets of continuum mechanics, applied mathematics, applied physics, and electrical engineering. A selected bibliography of books is given here below for the guidance of the reader. However, we wanted these lectures to be as self-contained as possible so that various appendices give the required information. Chapter 1 represents the rotationally invariant theory of nonlinear thermal piezoelectricity. It contains some necessary reminder on the theory of finite deformations of a solid. The important point here is the writing of the propagation equations in the reference frame. Chapter 2 concerns the one-dimensional bulk motion in linear and nonlinear elasticities. This has been used as an opportunity to recall some elementary results of wave propagation, to introduce the required technical vocabulary, and to exemplify various methods of applied mathematics in the study of nonlinear wave problems. Complements on the phenomenon of compensation between nonlinearity and dispersion are given in the corresponding appendix. Regarding the main results of this chapter, the reader should keep in mind that the fact that all methods of approximation yields essentially equivalent results for a short distance of propagation, while the multiple scale technique is certainly to be used if one wants to obtain solutions uniformly valid on a long spatial interval. Physically, the nonlinearities generate harmonics, and in the case of resonators, the wave problem on a finite spatial interval of a few wavelengths for which the straightforward expansion of the solution can be used, the phenomena of anisochronism, relative change in velocity of the fundamental frequency component, and intermodulation. Another cause of relative change of velocity is the nonlinear coupling between the crystalline and pre-deformation and bias fields. This is also examined since the effect can be in competition with anisochronism. The more technologically oriented case of surface waves is examined in Chapter 3. Here the propagation may occur over relatively long distances, hundreds of wavelengths, and the need for uniformly valid solutions is greater than for resonators. This surface wave problem in fact offers a beautiful problem of mathematical physics with a touch of engineering spirit in the simplifying assumptions made at the different phases of the solution. 1. Excitation of surface waves by means of interdigitated transducers, a problem of anisotropic electrostatics, provides an electric potential source of a rather complex form. 2. Emission of elastic waves. Through the direct piezoelectric effect, the above potential source generates a dynamical elastic displacement in the form of a surface elastic wave and so-called surface-skimming bulk waves. 3. Propagation in the substrate of an essentially elastic surface wave with linear or nonlinear behavior depending on the crystalline substrate. Harmonics can be generated and a parasite anisochronism may appear, and a detection of the propagating surface elastic waves through the converse piezoelectric effect, producing an elastic displacement source for the electric potential in an interdigitated transducer. Here also a nonlinear coupling between a crystal and a pre-deformation may cause a relative change in the velocity of linear surface waves. Finally, an engineering application, the surface wave guide convolver, is examined in Chapter 4 by way of application of the theoretical treatment. Here nonlinearities are essentially essential since they afford the phenomena of convolution. The involved solution is exhibited by using a numerical method, finite elements, based on a variational formulation of the boundary value problem. Special thanks go to my friends, Professor A. Morrow from Genoa and Professor Arcatesia in Stockholm for the very kind opportunity they offered me to deliver these lectures in the most profitable environment. Stockholm, 1912-1984, G. M. Maugin. Selected bibliography starts here, and there's A.C. Arongen of Mechanics de Continua, P. Germain, Cours de Mécanique de Milieu Continu, J.D. Achenbach, Wave Propagation Elastic Solids, E. Dulasant and D. Royer, Elastic Waves and Solids, Applications of Signal Processing, B. A. Auld, Acoustic Fields and Waves and Solids, M. Roseau, Vibrations des Systèmes Mécaniques, A. H. Nefe and D. T. Mook, Nonlinear Oscillations, O. D. Rudenko and S. I. Soluyan, Theoretical Foundations of Nonlinear Acoustics, A. H. Nefe, Perturbation Methods, I. A. Kunin, Elastic Media with Microstructure, E. Dulasant and D. Royer again, V. M. Ristic, Principles of Acoustic Devices, and Yuri I. Sirotin and M. P. Shaskolskaya, Fundamentals of Crystal Physics. They come from like Mir Publishers, John Wiley, Inner Science, Springer Verlag, John Wiley, Consultants Bureau, original Russian, John Wiley, Masson, Paris, John Wiley, Masson, North Holland. Contents reads off these four chapters. And I'll just read the introduction here of Chapter 1, Equations of Nonlinear Thermopiezoelectricity. 1. Introduction. In this chapter, we recall the essential developments of the theory of mechanically deformable continua, which are electrically polarizable and possibly heat conductors. They are neutral from the electric viewpoint, dielectrics, so that in contradistinction with, e.g., semiconductors, they do not exhibit a density of free electric charges and they do not conduct electricity. Our aim is the writing of propagation equations and associated boundary conditions which will describe the dynamical behavior when the material is subjected to excitations of arbitrary magnitude. However, the working frequency range is limited to a few gigahertz so that the influence of the magnetic field can be discarded, so-called quasi-electrostatic approximation. It is only with the rigorous development of nonlinear continuum mechanics and the introduction of certain methods of applied mathematics that the problems approached in the present series of lectures could be satisfactorily solved. Indeed, the nonlinear effects of interest require a good form and variant theory which only recently developed as a result of achievements by R. A. Japan, A.C. Arongen, H. F. Tierson, and others. Here below we only list a few works which are landmarks in this development on which the present presentation relies heavily. And he goes to repeat much same, and some books by Maugin and Collet, Thermodynamique des milieux continus electromagnetic avec interactions, Thermodynamics of the continuous milieu of electromagnetic with interactions, a general presentation using the principle of virtual power and the dynamical Galilean approximation for any magnetizable and electrically polarizable continua. The complete text with illustrations is given in a series of lectures delivered in 1975 in Poland, published as G. M. Maugin in Acta Mechanica. Here's journal articles from the Journal of Acoustic Society of America, Mechanics of Continua again from Krieger, Journal Acoustic Society of America, International Journal of Engineering Science, Journal of Physics, Relativistic Theories of Materials from Abraham, Springer Verlag, Tracts in Natural Philosophy, General Formulation, on the covariant formulation of the electrodynamics of continua, 4 parts from the Journal of Mathematical Physics, 1978. Maugin is very deep in the field. The following presentation is essentially based on references G, I, and the course given annually by the author of Paris University at the graduate level to the students in theoretical mechanics. The presentation of deformation theory is much compressed. He begins with motion and deformation of a solid, and then it begins, the introduction of at least at some point some formulas and stuff like that. He shows basically a mapping of this diagram, which results kind of the idea of displacement and motion. And then he gets into these various features that are representative of what are the concerns in what we have is called the classical and linear, which has got really good, easy solutions, is very well defined. And everyone who ever learned like the periodic motion of a spring and wave theory from this has been exposed to that. That then the nonlinear part is what happens when there are certain phenomena that basically result from a theory of potential, that the numerical methods at the linear part essentially lack solutions in their completions or closures. And so the nonlinear approach is a necessary thing because the mathematics that we get in school and through the course of a mathematics and an engineering and a physics degree have certain limits that get reached when their applicability begins to fail. And it's similarly in statistics and as it is in mechanics here, that there's a whole wide field of what's called the nonlinear, and really it's to reflect the completion of a fuller picture where the linear is solved in a lot of reducing terms of the area and approximations and numerical methods that eventually give out or fail, in terms of why then it's possible to get from a situation that these various forms, for example, matrix forms, or numerical methods having reduced terms to linear computations, that in terms of, like, for example, these complex values coming across various lines of integration or surfaces of integration, that it ends in results that it's possible to deal with the near field solution as it begins to introduce, and what happens when you have to deal with quantities of the infinitesimally small, and what that means when those powers essentially vanish, how they got there, so that we can deal with questions like what is velocity in terms of that it's displacement over time, in terms of then how is acceleration and its acceleration and its acceleration and all these higher orders of acceleration basically reverse of that from the nonlinear side, that it results in an approach that you can define one in terms of the other, because eventually what the goal is that the classical, which has defined like the inverse square, which is familiar as the formula for the attractive force of gravity, mass a product over inverse square distance, how it results that classical formulation is really a result of this nonlinear eventually, but of the theory of potentials, that the potential fields are the real fields. And what this refers to is that in electromagnetism, there's a lettered number of fields, and these are often called Maxwell's fields. And we're familiar with the basic field that's the electrical field and the magnetic field as B and E or D, and these are lettered, these fields, but these are these classical fields, we call them, while the potential fields start, for example, letter A is a potential field. That when these fields, after the summary solutions of Maxwell, that are of course entirely famous and are linear really, came to solve many or most easily computed problems in passive and active electrical circuits, arrived, that then there's also what's really underneath that, these systems of the fields in potential, which helps define why work and momentum and some of these other quantities that are defined in terms of where the potential energy is considered negative, and thus the real and the potential cancel out to zero, that instead the potential is what is real, and then the classical is what ends up canceling that out to zero at a given moment or an instant or as a vector or linearly. So what's going on here in this book is, first of all, he knows everything about linear analysis, and then he goes on to help describe what's going on. They found some empirical measures that help map and close these things for nonlinear analysis, and then he finds some few solutions that involve the exchange of coefficients, or otherwise the doubling spaces, or the application of particular methods in the formulas. This was what results then that it helps further and better explain that when these real world phenomena are put together in the laboratory and they don't match what are the plain linear formulaic approximations, that it provides for science and engineering a predictive value given these formulaic approaches. And so he's been working on this for about 30 or 40 years already. And today, and even these days, Maugin is over in France somewhere producing even more of these systems of what's going on in the series of waves. So later I'd hope to read, there's some later chapters that help describe these kinds of waves, and it helps us to get to where we've encountered in our study and learning. It's called particle wave duality. And we know this at the atomic level to give basically the linear moment of an atom that is a particle. But we know also that it's a wave because there's quantum mechanics involved, which really is continuum mechanics, and it's involved in where everything is energy. But then as we get above that to wave theory, then it results again that waves unify back to this form of resonance, and these days this is applied like nuclear magnetic resonance imaging, to where it remains kind of be seen how it's going to be made, so that it results from a quantum mechanics again to a continuum mechanics, because quantum mechanics is never wrong, of course. We just don't know much about it. It must be right. But that really it's a continuum mechanics to get to where it's possibly not wrong about continuum mechanics, and also to explain why in terms of the doubling spaces and some of the features of the infinitesimals, infinities, and the continuous and discrete, or the continua and their individua, which is of course its own kind of problem and challenge, and especially when you want to try to make a critical examination of the foundations of analysis, how to put that together in terms of what's called rigor and formalization to end up at formulas that basically suffice to demonstrate these things. Because, to tell you the truth, science has a lot going on and it has no idea how it got there. And so there's still a lot of empirical formula that don't really reflect a proper, rigorous, axiomatic foundation. And so questions and studies going on in this space of the nonlinear effects really are what going to make it possible in the future to have mathematics that people can understand and write down on a page, and that it doesn't end up that instead a giant cloud of computer cats thinks it in its empirical mind as an inscrutable form of oracle. So that said, now that's a few pages in why I'm so interested in Maugin and think I'm so great. And so hopefully then this will find you on a later afternoon. The globe is spun around a bit, and this shelf is here, otherwise about the same. We have Leonardo on painting, and differential equations, their solutions using symmetries. Symmetry is an approach, the history of the circle, where they might talk about the roots of unity, and also roots and powers as a general thing in terms of infinitesimals, infinity, and one, the unit. And this is this deconstructive criticism that we're going to talk about. It had a great quote about deconstructive theory, and why, on the one hand, it's not particularly relevant to anything, but on the other hand, it's just been gotten all wrong. So anyways, this nonlinear electromechanical effects and applications by G.M. Maugin has really got a lot going on, and it's a powerful primer to the study of further numerical foundations beyond numerical methods would arrive at, for example, a practicing electrical engineer or a scientist, how and why things work for continuum mechanics in a modern world where, once again, many of the theories like supersymmetry, real wave function, and all that comes from our knowledge and understanding of the incongruities or perceived paradoxes, or otherwise the confusing of quantum mechanics, and relativity for that matter, where quantum mechanics and relativity together basically make up physics, have that it results that this theory of potentials, which was key at least since the time that the great electricians lettered the fields of the magnetic fields, that it will so result that we'll be able to get to where it'll just be another regular course, and a lot of these things which today are very much state of the art, or as from the 60s, 70s, and 80s when mathematicians still had slide rules, that it so and so they were inclined to do things formulaically instead of computationally, that it results then we'll be able to again do this on paper and get it figured out. All right then, good afternoon again and good day.